So we're going to continue with the definite integral. So when you're thinking of the definite integral, you need to refer to the area problem. So basically the area problem was, I give you a function. I restrict that function to the closed interval AB, and I'm interested in finding the area under the curve from that function from A to B. So this area is what I'm interested in finding. So in order to do that, we broke it up into some subintervals. And right now we've talked about approximating that area using those subintervals and just using rectangles. Sometimes the area you get is an over approximation or an under approximation. Now we're going to move into actually doing it for real, an exact area. So in order to do that, our function needs to be defined on the closed interval. We divide the interval into n rectangles, subintervals. Right now we're going to focus on equal width. So if I have n rectangles, I take the distance between B and A and I divide it into n parts so that I get equal intervals to form the rectangles on. Now these don't necessarily have to be equal, but for this definition we're saying they're equal. What we do is we start with the A point and we label that x0. The next point we label x1, the next point we label x2, and we keep breaking it apart until we get to the last point, which is B, which we label xn. So we have n rectangles. So what we want to do is we want to figure out how we're going to form the height of the interval or the rectangle. And what we're going to do is choose a starred point. I'm going to call it xi stars to be the height of those rectangles. So we were talking about using the left endpoint method where we use the x naught to be our height or the x1, so forth. Now we're going to choose any point in this interval to be our x1 or x0 star or x1 star. And then we use the function value at that point to be the height. And then the definite integral is just defined to be an exact value. You take the sum of all the rectangles like we did with the approximation methods, but once you take the sum of all of them, you take the limit as the number of rectangles goes to infinity. Now, if this limit exists and it's the same value for all sample points, we can say that the function is integrable on A to B. So we've talked about what differentiability means. This is kind of like, what does integrability mean? Okay, what does integrability mean? Now we're not going to get into this definition too much because it's quite challenging, but earlier we said, how do you know if a function is differentiable? And then we had some key ideas to know. If I say, how do I know if a function is integrable or the ability to take an integral, this is what it means. It means that you can break it up, get that area, choose sample points, create a sum of all those rectangles, and then take the limit. Okay, now in reality, we would never do this by hand because it's kind of impossible. It's easier on computer programs and such, but you know, there are abstract statements you can write to show functions are integrable, but you don't get into that until later in math. Just a little history. This symbol is called an integral sign. So we can say take the integral of something. And if I don't put numbers on the integral, like here, this is just a symbol. As soon as I put numbers like the A and the B, we call it a definite integral. So I'll just write that down. So when there's numbers on it, we're doing a definite integral. And when there's no numbers on it, we're doing just an integral of the function with respect to x. This is the concept of antiderivatives, which is I1. Definite integrals are the concept of areas under curves, and that's I2. Okay. The reason you may say, why is that funny symbol used? They think of this funny symbol as an elongated S, and they do it because it was a limit of sums, and S is kind of like a sum, so they use a big, long, elongated S for that. Okay. Notation. So the f of x, we call that the integrand. The a and the b, we call those the limits of integration, a being the lower limit and b being the upper limit. Okay, so that kind of breaks up the x-axis into where we want the area between on for under the curve. When you look at the symbol dx, it doesn't really mean anything by itself. It's just kind of like saying that we're doing the integration with respect to x. Now, this integral, when we work this out, you need to know that this represents an area under the curve. Like, that's the big idea of I2. That I give you this symbol, and it means what function am I looking at, where do I start, where do I finish, and I'll shade in an area. That's kind of the big idea of I2. We develop I2 ideas by finding areas under curves and approximating them, and then we move away from it and then just move into actually solving these using algebra, okay? Now, the variable you use on the inside, so here they use x, it doesn't actually matter, it's just a variable to integrate with respect to. So this can be r's dr, t's dt, and so forth, okay? This fancy sum that we saw earlier, we call that a Riemann sum. Again, we're not going to get into the theory too much, but as you move up into higher level math courses, if you do, you will see these Riemann sums. So you kind of have to think, okay, these Riemann sums are used to solve that area problem, or at least attempt to solve that area problem. We're finding areas under the curve. We need rectangles to do it. We partition up our area into n rectangles of equal width, and then we just take either the left Riemann sum or the right Riemann sum or the midpoint sum or so forth. Okay, now over here, this definition of a Riemann sum, we work with the function on the closed interval. It needs to be defined. This delta is a partition, so that means I'm breaking up the rectangle, or I'm breaking up the distance from A to B into rectangles. But this time I call delta xi the width of the rectangle, and those widths do not need to be the same. The point I choose to create the height of the rectangle can be any point, and then we create the sum, which is called the Riemann sum. Okay, and again, the answer for all of these sums needs to be identical, because if it's not, you don't get this function's integral, and the function is not integrable on AB. So for us to have it integrable, we need the partitions to create the same answer when you take the limit, okay? If we take the limit, now in this case, we're not making the number of rectangles go to infinity. We're taking the sum of all the rectangles, but we're taking the largest partition. So let's say I break up my rectangle into unequal parts, okay? And let's just say that this partition is the biggest one. What we want to do is make this partition go to 0, because if I make that distance go to 0, all of these other ones will kind of disintegrate away. Okay, and again, if this limit coincides with every other value, then I know that the function is integrable on the interval a to b. Okay, now what happens if the function is positive? We know that when we're doing the area problem, my function is sitting above the x-axis. I break up this rectangle into sub-intervals, and I'm interested in finding the area under the curve. Now, all we've talked about so far is finding these integrals where the area lies above the x-axis. Okay, so this definite integral, we've always been getting positive answers for this area because it's a positive number. There's actual quantity there. Now, what happens if there's area that sits below the curve and some that sits above the curve? So what I would do is, if I call these three pieces area 1, and I call these pieces area 2, and I call these pieces area 3, when I do the definite integral from A to B, I'm doing A1, which is a positive area. Now, because this area lies below the x-axis, I need to subtract that area off. And then this stuff in blue is above the curve again, so I'm going to add it on. So when we do this integral, we're always doing a net change, okay, or a net area. So that means that stuff that sits above the x-axis, you add on that area. Stuff that sits below the x-axis, you subtract that area. If I was interested in doing the total distance or total area, then I would have to take this number, add on that number, and add on the last number, but I would need to take this area, reflect it to make it positive, but take the same value. Okay. Now, again, we've talked about dividing this interval into equal width, but we don't always have to have equal width. There are times where we will have unequal width, okay? And again, we take, if we have our intervals being different widths long, we take the largest width, the maximum of it, and we approach 0 with that maximum, okay? And then in this case, that Riemann sum becomes this. Okay, now this might look like a lot of sum formulas and whatnot. The idea behind it is just knowing what is the area problem and how to solve the answer to the area problem. That's what I expect you to know. I don't expect you to know too much into the depth of what's happening. Just here's an area problem. How do you solve it? You break your area up into rectangles. These rectangles can be equal or unequal width. The height of the rectangle depends on any point in that interval, and then if that gives you a consistent sum all the way through with all these definitions, then I know that my definite integral works and the function is integrable. Okay. Now this is a smart math guy rule that tells you when a function is integrable. So the function could be continuous, or in this case, the function doesn't even have to be continuous, but it has a finite number of jump discontinuities. So you can have a function that's integrable that is not continuous, but it needs to be a countable number. So I'm going to just say needs to be countable. So you can say 100 is countable, but infinity is not something you can count. Okay, then the definite integral of this stuff exists. Now, the majority of this lesson is just theory-based. Coming out of this lesson, you need to know sort of a little bit into what integrability means. You need to know how to solve the area problem, and maybe think about when is a function actually integrable. This is one way a function is integrable. Literally, most of the examples we do will be integrable. We're not going to deal with the scenarios that aren't, okay? If the function is integrable, then this definite integral, or the integral from a to b of f of x, or that area under the curve, will equal the sum. The delta x, or the length of each interval, would be b minus a over n. And again, if I start my interval at a and I want to get to the next point, I have to do a plus delta x. A plus 2 delta x, and you keep adding delta x until you get to the last point, which is b. Okay, one of the things I do expect you to know how to do is take an ugly sum limit expression and turn it into an integral. So we know they give you a closed interval. We know that that's our a and b, so I'm going to write a to b, which is 0 to pi. Now from here, you kind of look at what's happening and you remove all the i's and it will tell you what the function is. So this would be x cubed plus x sine x. And instead of writing delta x, we write dx because we're kind of doing it over all of them. Essentially, when that delta x literally is not like a finite rectangle, we take all those rectangles and make them infinitely small so that we're getting the total area. Okay, so literally this expression is the same meaning as this sum, provided the function is integrable, but they're just saying to express this as an integral, so you just take the sum and turn it into integral notation. Again, the context of this integral is area under the curve, and the point of this integral is to solve that area problem. So remember, we're taking the limit of delta and we replace it with the integral symbol. We take the xi's and just replace it with x. And we take delta x and replace it by dx. So literally that's all that's happening. That's the depth I want you to know with this sum notation, but you do need to know the approximation methods. Okay, so evaluate the Riemann sum for a function by taking the sample points to be the right endpoints, and they give you a and b. So what we're going to do is, this is an approximation. So we would go from 0 to 3. We break it up into 6 spots. So 3 minus 0 divided by 6 is equal to 1/2. So this would be 1/2, 1, 1.5, 2, 2.5, 3. So this would be 2.5 and 3. So you can see that this is 6 rectangles being formed. 1, 2, 3, 4, 5, 6 rectangles. Now the height of those rectangles, we want them to be the right endpoints. So my approximation would be 1/2 times the function value at the right endpoint. Now that 1/2 will be consistent everywhere. So I'm going to just do the function values at the right endpoints, and this will end up being our approximation. Okay, so f of 2 plus f of 2.5 plus f of 3. Okay, to find the answer, you're just going to take your function, you're going to sub in 1/2, so this would be 1/2 cubed minus 6 times 1/2. Then we're going to go 1 cubed minus 6 times 1, and so forth. Get that big, long, ugly decimal, and then write that answer down. Okay, again, this is a approximate value to the actual area. Example 4. Evaluate the following integrals by interpreting each in terms of areas. So you need to know, what is this function? This function is a circle, but it's only the top half. Okay, so if I look at the top half, I get x squared plus y squared equals 1. I rearrange, I get y equals plus or minus root 1 minus x squared. And then the positive means the top, and the negative means the bottom, and those two halves form your whole circle. So literally in this example, I have the top half of a circle. So I'm going to draw this out. This is my f of x. I'm interested in the area under the curve from my a to b, which is 0 to 1. So how would I find the stuff in yellow? Well, the stuff in yellow is just a quarter of a circle. So the integral from 0 to 1 of this function is equal to the area of 1/4 of a circle. And the area of a circle is 1/4 pi r squared. And in this case, my radius is 1. So this exact area is pi over 4. Now, when these shapes don't work out to exact values like this with simple shapes, we're going to do the same thing as we did in the first unit, and you'll start to see later on when we do fundamental theorem of calculus how you do this algebraically. Okay. Now again, this is the function y equals x minus 1. I need to sketch that function. So the x-intercept is 1. The y-intercept is -1, and I have a linear function. I'm interested in finding the area under the curve from 0 to 3. So let's say I go till there. So what I want to do is I want to do the area of the triangle plus the area of the other triangle. So let's look at the area of the two triangles actually. So I'm going to call this area 1. So area 1 is 1/2. My base is 1 unit long, and my height is 1 unit long. So the area of that is 1/2 base times height. But because that lies below the x-axis, that area would actually be negative. And area 2 is 1/2. My base is 2 units long. This function is y equals x minus 1. So when x is 3, y is 2. So this is 1/2 base is 3 units long. Or sorry, 2 units long. My height is 2 units. So that's 4 divided by 2, which is 2. So now my total area, this integral from 0 to 3 of x minus 1 would be equal to 2, which is the stuff that lies above the x-axis, minus 1/2, which is the stuff that lies below the x-axis, and we get an answer of 1.5 units. So you will have to evaluate integrals by using simple shapes. If I can use triangles and squares and quarter of a circle, half of a circle, a full circle, then there's no point needing to do areas. I mean, it's no point needing to do all this challenging work. Now, some properties of integrals. If you're doing a function and it's defined at some point A, and I ask you to do the integral from A to A of the function, that integral is just 0 because there's no space for under the curve. Like you'll go from A to the same point. There is no rectangle being formed. If I have two limits, so from B to A, and I want to switch those limits around, put my upper limit in the lower spot and my lower limit in the upper spot, you need to use a negative sign to do that. So let's look at these examples. It says evaluate these integrals. Well, the bottom limit is pi, the top limit is pi, so that integral goes to 0 by the property, the first property there. Now, normally we're used to seeing our lower limit on the bottom and our upper limit on the top, and it usually goes from smaller number to bigger number. I don't like seeing it from 3 to 0, so I'm going to switch it around, but then I'm going to leave a negative on the outside. And then I can evaluate this integral by using simple shapes. My y-intercept is 2, my x-intercept is minus 2. There's my function, and now I'm interested in finding the area under the curve from 0 to 3. So this area is a trapezoid, so the area is my height, which is 3 units along the bottom here. And then I do the function value at the first point, which is 2, plus the function value at the second point, which is 5, because 3 plus 2 is 5. And I divide that area by 2, and that's my formula for the trapezoid. So 7 times 3 is 21. 21 divided by 2 is 10.5, so my area is 10.5. So again, we're saying what is the value of this definite integral, and we're still evaluating them by using areas right now. Now, if I have sort of 3 coordinates on the x-axis, A, B, and C, and I was interested in integrating from A all the way to C, or B in this formula, what I can do is I can take an intermediate point C, okay? Instead of going directly from A to B, I can go from A to some intermediate point, and then from that intermediate point to B, and add those two areas up. This is called the additive property. So if I want to integrate the absolute value of x, what I can do is I can sketch the function. I'm interested in finding the area from minus 1 to 1. So what I can do is I could go from minus 1 to this intermediate point 0 of the function, plus I can go from 0 to 1 of this intermediate function. And now I can work these out. This is the area of a triangle, 1/2 base. When x is 1, y is also 1 or negative 1. In both cases, the y coordinate will be 1. So that's 1/2 times 1 times 1. And then from 0 to 1, I get another triangle. The base is 1/2, or 1/2. The base is 1. The height is 1. So I add a 1/2 and a 1/2, and I get 1 unit. So my total area under the curve is 1 unit. But to evaluate it, I used 2 parts. I went from minus 1 to 0, and then from 0 to 1. Now, just like before, if you have some constant with multiplying by the function, you can sort of ignore the constant, do the integral of what you have, and then multiply your answer by the constant. And if you have two functions being added, you could do the integral or area for the first one, and then whatever the symbol was, add or subtract, and then do the area of the second one separately, and you don't have to add the functions first. Okay, so let's look at how this property works. If I'm doing the integral from 1 to 3 of minus x squared plus 4x minus 3, I can break it apart. The minus is a constant, x squared dx, plus I'm going to go from 1 to 3. The 4 is a constant, and then the x is part of the function, minus the integral from 1 to 3 of dx. And the 3 is a constant, so I'm just going to pull it out. Okay, so we know that the integral from 1 to 3 of x squared dx is 26 over 3, so this would be negative 26 over 3, plus 4 times the integral from 1 to 3 of x dx is 4, so this is 4 times 4, minus 3 times the integral from 1 to 3 of dx is just 2, and then I just work out this final answer as a fraction or a decimal. I'm just going to turn it into a simplified fraction here. So when I do that on the calculator, I get 4 over 3. So that would mean if I were to draw this quadratic and take the area under the curve from 1 to 3, I get an answer of positive 4 over 3, regardless of whether I do each piece separate or think of the whole function as one. Last thing, if I have a function and it's integrable and non-negative on the closed interval, so that means my function is always positive, then the area under the curve is also going to be positive. So this is just saying area is positive, provided that happens. If you have two functions and one function is always less than or equal to the other function, then the areas are also true for that. Like the area under the curve of the smaller function will be smaller than the area under the curve for the larger function. Okay, so again, the primary point of this lesson is just to kind of get the properties of integrals. You need to know your properties, which are the ones we just went through, how to apply them. You have to understand what a function is integrable means and be able to explain that. Okay, and then other than that, most of this is theory, so you can kind of think about the theory, but I won't be asking specifics about the theory.